Norway is not a huge country. Australia is about 24 times larger, but depending on what you count, Norway's coastline can be reported as longer than the entire equator. And the weirdest part is, nobody is cheating. They're just using a different ruler. Because the length of a coastline is not one fixed number. Measure it with a long ruler and you skip the tiny bays and curves. Measure it with a shorter ruler and the coastline gets longer. Measure every inlet, every rock, every crack in the shore, and the number keeps growing. This is called the Coastline Paradox, and it means a country does not have one true coastline length independent of scale. Which is awkward, because coastlines help shape maps, borders, fishing zones, oil claims, and billions of dollars in ocean rights. So here's the strange question. How long is a country really? The story begins with Louis Fry Richardson, an English mathematician with one of the strangest obsessions in science. He wanted to understand why nations go to war. Not emotionally, mathematically, because apparently some people see centuries of human conflict and think, interesting, let's make a spreadsheet. Richardson was a Quaker, a pacifist, and a man who believed that even war might have patterns if you collected enough data. So in the 1940s and 1950s, he started studying borders, how long they were, where they were, and whether countries with longer shared borders were more likely to fight. But while collecting data, he noticed something bizarre. Portugal said its border with Spain was one length. Spain gave a different number for the exact same border. Same land, same mountains, same rivers, same line on the map. Two different lengths. And this was not because one country had lost the ruler behind the sofa. The problem was deeper. Richardson realized that the measured length of a border depends on the size of the measuring unit. Use a long ruler and the line looks shorter because you cut across small bends. Use a shorter ruler and you catch more detail. Use an even shorter ruler and you catch even more. The line keeps getting longer. And natural borders, rivers, mountains, coastlines are especially messy because nature did not design itself for government paperwork. Richardson plotted the data and found a pattern. As the measurement unit gets smaller, the measured length increases, and for rough natural shapes, it may not settle neatly into one final number. This was not just a surveying problem, it was a scale problem. The answer changed because the question was incomplete. Not how long is the border, but with what ruler? Richardson's work was mostly ignored at first. Then, in the 1960s, a mathematician named Benoit Mandelbrot found it. Mandelbrot was working at IBM, surrounded by early computers, strange patterns, and the kind of mathematical weirdness that normal people quietly leave the room. He looked at Richardson's coastline problem and realized something profound. A coastline is not a smooth line. It is rough at every scale. From space, a coast may look like a simple outline. Zoom in and you see bays and headlands. Zoom in again and those bays contain smaller inlets. Zoom in again and the rocks have cracks. Zoom in again and the cracks have smaller edges. The detail does not disappear, it multiplies. Mandelbrot gave this kind of shape a name, fractal, from the Latin word fractus, meaning broken or fractured. A fractal is a shape that shows complexity across scales. A small part can resemble the larger whole, not perfectly like a copy-paste button from nature, but statistically in the same rough pattern. This was the key. The coastline is not a smooth line you learned at school. It is not a triangle. It is not a circle. It is not a polite little shape waiting to be measured. It is a rough, natural boundary between land and water, shaped by glaciers, waves, erosion, rocks, tides, and time. Basically,
Earth looked at Euclidean geometry and said, "No thank you." In 1967, Mandelbrot published a famous paper with a title that sounds simple but is actually a trap. How long is the coast of Britain? His answer was not a number. His answer was, "It depends." And that's what makes the paradox so powerful. A coastline can have many correct lengths depending on the scale of measurement. With a 100-kilometer ruler, Britain has one coastline. With a 10-kilometer ruler, it has another. With a 1-meter ruler, it has another again. The coastline did not change. The measurement did.
At this point, you might be thinking, okay, so coastlines are weird. Nice math trick. But this is not just a math trick. It matters because coastlines are connected to power. Under modern maritime law, what really matters is not just the total length of a coastline. The crucial concept is the baseline. A baseline is the line from which a country measures its territorial sea, its exclusive economic zone, and other maritime rights. So from that baseline, a country can claim territorial waters. Farther out, it may have rights over fishing, seabed minerals, and offshore oil and gas. So the question is not simply, how long is your coast? It is also, where exactly does your coast begin? And that gets complicated fast. Take Norway. Its mainland is carved by fjords, long, narrow inlets cut deep into the land by ancient glaciers. Add islands, skerries, and tiny coastal features, and the measured coastline can change dramatically depending on what is included. Canada is even more extreme. It is commonly listed as having the longest coastline in the world, mostly because of its massive Arctic archipelago. But even that famous number depends on definitions, scale, and measurement method. Indonesia, the Philippines, Greenland, Russia, Japan, all of them have coastlines where islands and rough shorelines complicate the numbers. And once islands enter the story, things get even more political, because in some maritime disputes, a tiny island, reef, or rock can affect how ocean zones are argued. Sometimes a tiny feature in the sea can be worth more than a beautiful beach, which is unfair to beaches, but very typical of geopolitics. In places like the South China Sea, countries argue over what counts as an island, what counts as a rock, what can generate maritime zones, and where baselines should be drawn. In the Arctic, melting ice is opening shipping routes and making resources more accessible. The shape and status of coastlines, islands, and seabeds can matter enormously. So the coastline paradox is not just about a funny ruler. It shows that measurement is never completely neutral. Before you measure something, you have to decide what counts. And when what counts can affect oil, fish, trade routes, and national borders, people tend to become very interested in the ruler. The coastline paradox is not limited to coastlines. Richardson first noticed the problem with borders. Natural borders often follow rivers, mountain ridges, valleys, and shorelines, all shapes full of irregular detail. And the same kind of scale problem appears all over nature. How long is a river? That sounds easy until you ask whether you count every bend, every side channel, every seasonal shift, every tiny curve at the bank. How large is the surface area of your lungs? Much larger than it looks because the tissue is folded into tiny branching structures designed to maximize surface area. Nature loves folding, which is beautiful, efficient, and extremely annoying for anyone trying to make a clean table of numbers. Mandelbrot's deeper insight was that the natural world is not mostly made of clean textbook shapes. It's made of roughness. Clouds are not spheres, mountains are not cones, rivers are not straight lines, coastlines are not simple curves. The world is jagged, folded, branching, broken, and self-similar across scale.
That does not mean measurement is useless. It means measurement always has rules. A number is not just a number. It's a number produced by a method. Change the method, and sometimes you change the world you think you're describing. So how long is the coastline of Norway, or Britain, or Canada? The most honest answer is, there is no single answer without a ruler. Measure from space, and the world looks simple. Move closer, and the simplicity breaks apart. Move closer again, and the map becomes a maze. The Coastline Paradox teaches us something strange about the planet. The line between land and sea is not really a line. It's a negotiation between scale, water, rock, law, and human patience. And hidden inside that line is a bigger truth. The world is not as neat as our maps want it to be. It's rougher, wilder, more detailed, more fractal. And sometimes the most important thing about a measurement isn't the answer, it's the ruler. If you like stories about maps, borders, hidden systems, and the weird rules that shape the world, subscribe to Global Facts. And tell me in the comments, what is the strangest thing a map has ever taught you?